In this video, we're going to look at two-body problems. Two-body problems take what we know about Newton's first and second law and what we know about Newton's third law and kind of put it together, allow us to predict behavior of a system with more than one object in it. So the classic example of a two-body problem is an Atwood machine, sometimes called Atwood's machine. But it basically consists of two masses and either a pulley or a set of pulleys over which a string is hung. There's a lot about them that we can get into, and we will, but this is a two-body system. When we are talking about a two-body system like this green dog and yellow dog, there are a couple of assumptions that we are making, at least initially. That this is an ideal pulley and an ideal string. And for an ideal pulley, what we mean is it's a massless pulley and it's totally frictionless. An ideal string is also massless and frictionless. The ideal string is, for most of the strings we use with decent sized masses, a really good model. The ideal pulley, we have some very low friction pulleys, very low mass, small moment of inertia, so that works well. We'll address what happens if that's not true as we go in a little bit later. The other thing that is important is that the string is not stretching at all and the force of tension is the same everywhere in the string. So that means we don't have to draw a free body diagram for either the string or the pulley because we're kind of ignoring them and letting them be something that changes the direction of the tension without doing anything else. So if we release this system from rest and we say a couple things, say the mass of the green dog is bigger than the mass of the yellow dog. Well, what can we say about the motion? Well, if the mass of the green dog is greater than that of the yellow dog, we would say, oh, the yellow dog is going to accelerate up and the green dog will accelerate down. The acceleration should be constant because there are these constant masses, and that they both should have the same acceleration. After all, they're connected by that string. You can't have one go up without the other one going down. The acceleration also must be smaller than the acceleration due to gravity because they are not in free fall. And that's the fastest anything can accelerate without being pulled downward. More on that in a moment. If we were to draw our free body diagrams, we would see that they both the green and yellow dog experience a downward gravitational force and an upward tension force. We know that the force of gravity on the green dog has to be greater than the force of tension because it accelerates down. We also know that the force of tension has to be bigger than the force of gravity on the yellow dog because the yellow dog accelerates up. We also know that the force of tension is the same on both. That's what we said from Newton's third law. That is a third law pair. So we can put all that together and say that the force of gravity, or the weight of the green dog, is bigger than the force of tension on the green dog, and the force of tension is greater than the force of gravity on the yellow dog. We can put all this together to actually solve a problem. For example, we have a 10 kilogram mass and a 5 kilogram mass here. And if we're going to solve a problem for the acceleration and all the forces involved, we need to be able to identify our objects. So the first thing to do is label those objects, 1 and 2. Then we want to draw a free body diagram for each of them. Object 1 has tension up and the force of gravity down about 100 newtons. Object 2 has a force of tension up and the force of gravity down about 50 newtons. The last piece before we jump into actually using Newton's laws is to identify the action-reaction pair. And in this case, it is the force of tension. So this is sort of a little hash mark saying that these two forces are the same. Sometimes I circle them. Sometimes I write a little note. These two forces are the same. But you need to identify them in some way. Now we want to label the coordinate system. This is something we always do. And we have a couple of options. We could call up positive, down negative, and then they're each going in opposite directions. But we might change that up and say, let's call the direction of motion the positive direction. So up is positive for object 2 and down is positive for object 1. This simplifies our problem solving a little bit, as we'll see. So now we can write out two Newton's second law equations. The net force on 1 is m1a, net force on 2 is m2a, and we can write out that that is the force of gravity minus the force of tension, and the force of tension minus the force of gravity for each of those masses. We can then combine these equations to solve for the acceleration. If we eliminate the force of tension, where we've got a positive and negative, we add them together, then we can say that the acceleration, which is the same for both as well, can be solved, and it ends up being about 3.3 meters per second squared. You might ask yourself, does this make sense? Well, it is less than the acceleration due to gravity, which is good, and it is also more than the acceleration would be, or sorry, less than the acceleration would be if you just had a 10 kilogram mass being pulled in one direction by 50 newtons and one by 100, because we have more mass in the system. There's a total of 15 kilograms of mass, which shows up in the denominator here. Next step would be to solve for the force of tension. It turns out you can pick either of your two equations. Both have the force of tension in them. Solve for the force of tension, plug in your known values, and you get a particular answer. In this case, 65 newtons. Does this one make sense? Well, we already said that the force of tension had to be smaller than the weight of object 1 and greater than the weight of object 2, and 65 newtons fits the bill. We could then solve a kinematics equation for this. Say, how long does it take to reach the floor 3 meters below? Plug in the acceleration and solve. There are a few other types of problems we can solve. This is packet pages 30 to 31. We'll do some of this in class. But if you look at step 3 here, it can be helpful to call the direction an object moves the positive direction. Now, for the Atwood machine, that meant up is positive for one and down is positive for the other. But for this example, we could call to the right positive and along the incline positive. So now we still have one-dimensional motion for each object that we care about. That's what's nice about pulleys. They're basically magic devices that change the direction of the force of tension. We can do a little bit more, though, because we've already seen that if you set up the two equations and you solve them, two equations, two unknowns, you can get there. But there's another method that can be a little bit simpler. So we're going to look at problem 1 from page 30 if you want to follow along. And in this problem, we are going to treat the entire system as one object. This is sometimes called the sock method or the snake method. Basically, what you're doing is you're encapsulating all of the masses that are connected to each other in something and saying, whatever's inside, we're going to ignore. These are the internal forces, action-reaction pairs, and they cancel out inside. And only forces from the outside acting on this can actually cause the system to accelerate. And in this case, that's just the applied force of 25 newtons, or tension force, whatever you want to call it. The system boundary is important. That's my dotted line showing what is inside and what is outside. And so this could be considered the worm, the snake, the sock method, whatever you want to call it. But what we're going to do is we're going to find the acceleration here by saying we got a normal force on the whole thing. This is the entire mass times little g. And we have an applied force of 25 newtons. To find the acceleration, we're just saying the net force in the x is ma. The applied force is 25 newtons. The total mass is 42 kilograms. We get 0.6 meters per second squared. And then we can go back and do what we've done before and say, well, for each of these objects, we could write out a Newton's second law equation, right? The force of tensions are the same. And if we look at object 1, which is being pulled by this internal tension, that will very quickly allow us to solve for the tension. You could use either one, but that's probably the fastest one, right? Because it is force of tension equals ma. This time that mass is going to be equal to 12 kilograms times the acceleration, giving us 7.1 newtons. We could check and do it for the other one, right? 25 newtons minus 7.1. Divide that by the mass of 30 kilograms. Does that give you the same acceleration? Yes, it does. So another way to think about this is look at problem 1 again. There's part A and part B. So if the only thing we do is switch the masses, the 30 kilogram goes to the back instead of in the front, what stays the same and what changes? Well, the things that are the same are that the same amount of mass is inside and the same net force or outside force is on it, the applied force. And then that means the acceleration of the system will be the same. What changes? Well, the internal tension force is different, which means that the force of tension that we would measure if we were to put it in a spring scale would be different. And this is because the trailing mass doesn't need as much tension in the first example as it does in the second, because its mass is different. There's another interesting sort of the bricklayer's disaster, which is a fun video to watch. I'll leave this to you if you like, that talks about this kind of two-body problem. To wrap up, remember two-body problems use Newton's first, second, and third laws together. You can solve them in two ways, a system of equations or the sock, worm, snake, treat system as one method.